Let's talk about how object hierarchies are held together. Office documents have lists of pages and page contents. GUI consists of forms and controls. Databases have tables and indexes. Compilers operate on abstract syntax trees. All these data structures have something in common: they are organized in a tree-shaped hierarchy, where each object has exactly one owner. This type of relation is a well-known composition. In UML it's portrayed as a filled diamond arrow. Argentum has a special composition pointer: the owning pointer. Every time you declare a class field initialized with a class instance, it's an owning pointer field. These two declarations look similar but they are slightly different. This one is a local temporary pointer, while this one is a owning pointer field. Two temporary pointers can reference the same object, but owning pointers cannot. If allowed, it would violate composition single-parent invariance. This expression yields a temporary stack pointer, but only owning pointers can be assigned to owning pointers. A rule of thumb: a local owning pointer is created by expressions that produce a new, unowned object. This includes creating a new instance, copying an existing object, or returning a new instance from a function or block. Argentum has the built-in copy operation for object hierarchies. It works with maximum correctness and memory and space efficiency. It makes a deep copy of the object hierarchy, because shallow copy violates composition invariance. And Argentum's goal is not only memory safety, but also the higher-level object hierarchy safety. Copy operation is much more than just a deep copy of a tree. It supports other types of pointers, it backs const safety and multithreading. We'll revisit it later. What happens to the previous value stored in this field? It is disposed immediately if not retained in some temporary pointer. And this destruction affects the whole subtree. Sometimes objects retain external resources, fonts, sockets, file handles. Argentum allows defining after copying destroy functions that automate resource lifetime handling. In this example, file is closed when the parser goes out of scope. In most real-life cases, an object can have a variable number of child nodes, a document can have an indexed list of pages and a key-value set of styles. It's represented with an array and map of owning pointers. All operations on collections items are totally identical to the operations on scalar owning pointers. What about memory leaks? Owning pointers manage tree structures, handling creation, disposal, assignment, and deep copy operations in a way that prevents pointer loops. An object subtree lives as long as its root is accessible via a temporary pointer. Since, as proven in the previous chapter, temporary pointers are destroyed when they go out of scope, owning pointers ensure no memory or resource leaks. You may say that application data structures are not reducible to trees. You are right, there are types of object relations other than composition. We'll discuss other pointer types in the next chapter.